Hello. In this video, I'm going to explain problem 24 from the 2015 F equals ma contest. We are given the formula for the speed of a transverse wave on a long cylindrical steel string. This is a formula in general where the speed of a wave is equal to the square root of t over mu, where mu is the mass per length density, and that's exactly what we're given here. But since they've given it to us, we don't need to memorize that. And we are told that we have two steel strings of the same length, and the second one has 4 times the radius of the first, and each string is tightened to the maximum possible tension without breaking. And we are asked to find the ratio of their fundamental frequencies of vibration. So first we should discuss what is a fundamental frequency. Fundamental frequency. So suppose we attach the string to 2 fixed ends, so the ends of the string cannot move, and so only the string can, the points on the string can move up and down, but not left and right. Then what will happen is that the string will have certain allowed standing waves, and basically these will be sinusoidal waves. So the first one will look like this, and of course it will oscillate up and down, so it'll sort of go up and down. It'll basically oscillate up and down like this, but it's called a standing wave because the wave, as you can see, doesn't actually travel anywhere. And then you would have that first one is called the fundamental, which is ultimately what we're going to be talking about. It's also called the first harmonic. These are called harmonics in general. And then you would get a wave like this, which sort of has 2 peaks, and of course it would oscillate the other way as well. And so this is called the second harmonic. Then you'd have one that oscillates 3 times, so I'll just draw one more. So not sure how accurately I will be able to draw this, but it should look something like that. Probably not exactly the best drawing, but it should be good enough. And so on, and you'll have higher order ones, higher harmonics as well. So what is the frequency of this fundamental? Well, we know that the frequency is equal to the velocity divided by the wavelength. That's true of any wave. But what is the wavelength of the fundamental? Well, if you look at the fundamental, this form of the wave is just half of a sine wave, which means that this length L of the string is just half the wavelength, meaning that lambda is just 2L. So we got F is equal to V over 2L. Now, L is the same for both strings, so we just need to find out how V equals the square root of T over M over L, so it'll be TL over M, varies for the 2 strings. Well, we know that the mass is proportional to the cross-sectional area of the string, which is then proportional to the radius squared, and which means that since R2 is equal to 4 times R1, then M2 will be 16 M1. But we also know, and this is something that unfortunately you would have to know, and this is definitely not something that's immediately obvious. And so I definitely feel that if you didn't know this fact, then you would basically be unable to solve this problem. And I don't think there's a particularly easy way to figure this out just intuitively. That the maximum, so we're told the strings get extended or are stretched to the maximum tension that they can sustain without breaking, and it turns out that that tension is also proportional to the cross-sectional area. In fact, it's equal to something called a tensile strength, which has units of pressure multiplied by the area, and thus this means that the fraction T over M is actually the same for both strings. for both strings. And that means that actually V will be the same for both strings, meaning that F equals V over 2L will also be the same for both strings, since they both have the same length. And thus, the ratio of their frequencies is equal to 1, or the ratio of their fundamental frequencies. All right, thank you for watching, and I hope that was helpful.